Okay, so now let's take some time to talk about equation number 9 in this famous paper by Nelder and Wedderburn. The link to this paper, if you want to read along, and the link to the complete playlist that I'm making for this paper are included in the description of this video. Okay, so what's going on in equation 9? We have the Newton-Raphson process with the expected second derivative for a sample of n. It gives all this stuff here. I went ahead and wrote this on my blackboard. Before I move to my blackboard, I want to point out they wrote this sum sign here, but they didn't write that it is k equals 1 to n. That's what it should be. We're summing from k equals 1 to n. And then also z should have a subscript k. So you'll see I've marked those in blue here so that you can just make sure you're clear with that and clear with your notation. Okay, so we have up top here, I just want to write down some results that we've previously found. So this is our first derivative of the log likelihood, and this is an element of the Fisher information matrix. And we talked about this previously in this playlist, so I just wanted to include those because we'll need that for sure as we talk through what's going on here in equation 9. Okay, so before I actually talk too much about equation 9, let's start with the Taylor expansion. Let's just, before we dive into exactly what's going on here, let's just go in memory lane and remember good old Taylor expansions. All right, Taylor expansion around, say, a number a. That says that f of a, okay, so you wanted to know what f of a is, and Taylor was like, okay, we'll take a guess, and then the derivative at that value, at that guess value, and then that'll be a minus x here, and then there was like plus some residual, which you could actually just write this is approximately equal to, and then you can get rid of that residual. Okay, so that's basically what Taylor's expansion said. And then Newton-Raphson came along and said, hey, I can use Taylor expansion to find roots. So Newton-Raphson method to find a root. Basically, what is a root? A root is the value of a such that f of a equals 0. So you'd say, okay, well, what is a, right? So that's what you would want to solve. You would want to solve for a. So I could have this equation, this Taylor expansion equation. And what I could do is I could use algebra and rearrange it and solve for a. Okay, and that's what Newton-Raphson did, basically. Then Fisher comes along, and then he's thinking about how to use this to solve our likelihood problem, which, what is our likelihood problem? Well, we have a likelihood, likelihood function, and the derivative of that likelihood function with regards to our unknown parameter, we want to find the root. Okay, so for what is beta j, so that derivative equals 0. That was our question, right? That's basically what maximum likelihood is. Remember, maximum likelihood, if we have our likelihood function, we have beta over here, we want to find where the derivative equals 0 because that's where the max happens. Okay, so you set the derivative equal to 0 and solve. In this case, we can't solve it closed form, so we're looking for some sort of iterative method to solve it, and that's where this comes into play. So we're trying to think this through. Now we have n observations. Previously, every time we've discussed this, we've only had one observation. So how do we deal with that? Let me just remind us what is our likelihood function. So this is kind of like a side note. Because now we have more than one observation, we need to think about that. So we have our likelihood is basically the log of our density function for our random variable z. let's see, was it, I think it was theta and then phi. Okay. Now if I have more than one value of z, that's, now I have n observations, and they're n independent observations. So our function, we could just, when you have independent observations, you could multiply your density function by itself, right? So let me write this like this. Okay, this capital pi stands for multiplication. So from k equals 1 to n. Okay, so this is the likelihood function when I have more than one observation. So up until now, we've only ever had one observation, but now I have more than one observation. They're independent observations, so that's why I can just take the product, and that will be my density, my joint density function, Okay, so then when you have a log of a product, that's the same thing as the sum. From k equals 1 to n, the sum of the logs. Okay? All right. So up until this point, we basically have talked about this only with regards to one value. So we could think of that as Lk. And now L is our joint density when we have more than one observation. Okay? So that's a little side note. Very important now because when I write L, the derivative, this derivative here of the likelihood, really what I'm writing is the sum of all of those individual likelihoods from k equals 1 to n. Okay, that's what I want to equal 0. All right. Okay. So then, where am I going to go from here? Let's recall. I have 0 equals f of x plus f, the first derivative of f of x, a minus x. Right. This is our Newton-Raphson, who said, okay, if you want to find this, just go ahead and plug in 0. Now we have this. We don't have f of x. We have the first derivative. So let's plug that in, okay? So I have, this is the function I'm trying to find the root of, okay? And then the derivative of the first derivative would be the second derivative. Beta I, beta j. Okay. Then I would have, instead of writing a minus x, basically that's our change in the value that we're plugging in, right? So another way of thinking about this is like change in x, right? So sometimes you'll see this written as delta x. Well, in our paper, they use delta. Instead of, they use a lowercase delta, and they write delta beta, let's see, it should have been I, right? We usually start with I, and then we use j second. So this is I. Yeah. Beta I. Okay. Okay. Let's see. We're getting really close to equation 9 now, actually. So, what I want to do now is I want to go ahead and move this part to the other side of the equation. So I'm going to go ahead and subtract it from both sides using little algebra. So I'll have negative. Actually, I'm going to move that sum out first. So I'll have the sum from k equals 1 to n, and I have negative that second derivative okay, our change in beta, delta beta, change in beta. K equals 1 to n. Okay. So now I can plug in. Well, actually, no, sorry. Before I can plug in, Fisher said basically we can't use this. What we need to do is we need to use the expected value. So that's how Fisher's information comes in. So instead of doing this, we do negative the expected value. Okay, and then everything else stays the same. So that's where we have Fisher's information from. Right. So this was Fisher's information. All right. So now I can plug in. I can plug these in because these, if I go back up to the top, these are right here. Now up here, I don't have the subscript k, so let's talk about that k. That k will come in and it will be here and it will be here. Okay. And it will be here because there's different values of x for different observations. There's different values of z for different observations, and there's different values of w for different observations. Okay, so now I can just plug and chug and see what I get. So let's scroll down. I'm going to go ahead and plug that in here. Okay, I have alpha of phi, wk, xik, xik, change in beta equals k equals 1 to n of alpha phi xik zk minus mu divided by d mu dy. Okay, so then this alpha phi does not have I, so it can be pulled out of the sum, and then I can divide both sides by it, so basically it cancels. Okay, so that's really nice. xik, xjk, change in beta I, k equals 1 to n, xik, zk minus mu divided by d mu dy. Okay, so then from here, this is basically what equation 9 says, except now they've decided to go ahead and use matrix notation to make life a little easier on them. Okay, so instead of having beta I, they have a vector of betas that is an m by 1 vector. Okay, because remember there are m parameters. Then they have an a, which is, so this is delta change in, so you're taking the change of each element of the vector. And then they have a, which is an m by m matrix, where recall aij is this basically what you have right here. Okay, from k equals 1 to n, so you can see it right there. All right, that's how they've defined A. And then they say that this equals C, where C is a m by 1 vector. So the ith element of C is exactly what you see up here. From k equals 1 to n, wk, xik, zk minus mu divided by d mu dy. Okay, so they're just using matrix notation there at the end, but that's basically what how they arrived at that equation there.